So I'm going to try to shift a little bit, and I think we're going to move from geometry and pattern and design into structure and mechanics. I think a lot of people have mentioned the parallels, analogies of certain geometries used in nature, and patterns in nature has really been a question that has driven man's creative spirit for generations, thousands and thousands of years. But I think one thing Fuller talked about is really trying to understand the design principles behind how you build those patterns, rather than just what do they look like. And the example I always give is there's lots of ways to build a model of a dinosaur. You could have an injection molded plastic brontosaurus that looks a damn lot like a brontosaurus. So you could go and get wooden slat models where you stick them in and they look like a brontosaurus. Or you could use fractals and you could make, you know, Jurassic Park, and it even moves like a brontosaurus. But there's only one way that nature built a brontosaurus, and that's with muscles and bones. And I'm going to basically approach the same question of how nature builds as a biologist, because my lab for over 30 years has basically been interested in the question of how living cells and tissues are constructed so that they exhibit their incredible organic properties, including the abilities to change shape, move, and grow. Now, as you probably remember from elementary school and high school, you tend to think of the cell, which has a membrane and sort of a viscous gooey cytoplasm, has a viscous gooey cytoplasm surrounded by an elastic membrane, or as I always like to say, a water balloon filled with molasses. However, it's hard to envision, if cells are built this way, how they can do the things they need to do to form the embryo and to keep us functional. For example, Casper showed a static image of development yesterday. At the right, I'm going to show you a movie of zebrafish development that occurs over 24 hours. This is the yolk sac with the eggs have just divided and they're 2. Now they're 4. Now they're 8. And then they're 16. And then they're 32, 64, 128, 256, and so on. And they're getting smaller and smaller and smaller. But then they hit a point where they don't get smaller. And now they start pulling on each other and pushing and twisting and bending and folding and transforming. And this is all driven by the power of cells pulling on other cells and molecular lattices they put out. Here's the eye up top and the spine and the yolk sac in the middle. Furthermore, all adult tissues sense mechanical forces and remodel themselves to optimally function in minimize stresses and strains, the effects of compression on bone, fluid shear forces, and wall tension on your blood vessels are some simple examples. But cells also, we know, can generate tension. You can't do this with a water balloon filled with molasses. And this is true in muscle, and this is even cells on a dish. These are cells on a flexible substrate.